Hello my shimmering stars, today I Shaurya Grover welcome you all to this amazing platform of PW English. So yes my dear students, today we are going to start with lecture number 5 based on the chapter Coordination Compound under our batch Excellence Batch. I hope so students you have seen the previous lecture and all the topics were clear to you. So today we are going to proceed to the last lecture of this chapter, that is Coordination Compound. Students, before going on to this session, let me tell you one thing. Be a good student. Be a good student. Learn as much as you can. Always be willing to grab education, for the time is at hand. Study your books and strive to be the best. Study your books and strive to be the best. Focus on your studies and be a cut above the rest. So hello my shimmering stars, with this quote we shall start our today's session, that is lecture number 5. Now what are the segments that we are going to cover in this particular session? See students, we have almost completed with the crystal field splitting energy, the crystal field splitting theory in the case of tetrahedral, square planar complex as well as the octahedral complex, which hold a very large part of your syllabus and is really very important with respect to your examination. So today students, if you remember in the last lecture we had started about isomerism. So today we are going to cover that first of all. So what are the topics to be covered? So first of all students, we shall finish with the isomerism section. We shall finish with the isomerism part. After that students, we are going to understand about the bonding in the metal carbonyls, okay, and at last we are going to do the practice session. And at last we are going to see the practice session. So students, let us start with the very first segment of ours today, that is going to be the isomerism, okay. So before going on to the isomerism, there are certain questions that are generally asked from the colored complexes topic, okay. So let us talk about a certain question. For example, if I say you CuSO4 is colorless while CuSO4 dot 5H2O is a colored compound and its color is basically blue. So you need to tell the reason. Why is it so? My question to you all based upon the colored complexes topic is that CuSO4 is colorless, while if I talk about CuSO4.5H2O, it is a colored compound. Basically, sorry, it is blue in color. So what is the reason behind it? See, basically what happens, we had initially made the transitions, we have already seen that there are two kinds of, energy levels. One is the T2G, another one is the EG level, in which we used to fill the electrons. Am I right? Now students, when I'm talking about these two compounds over here, if I initially talk about the very first compound, that is about CuSO4. So CuSO4 students is a kind of a simple salt. And in the cases of simple salt students, there is no DD transition. That means electron will not move from one energy level into the another energy level. So there is no DD transition. No DD transition that will occur in CuSO4 because it is a simple salt. But if I talk about which one? If I talk about CuSO4 dot 5H2O students, it is a kind of a coordination compound, or I would say the complex salt, okay. It is a coordination compound, or I would say the complex salt. Now, as it is a coordination compound or a complex salt students, over here DD transition will occur. That means electrons from one energy level will move on to the next energy level. right? From lower energy level, the electron shall move on to the higher energy level, and when it will move from the higher energy level, it will emit some kind of energy, and so it will provide color to that species. So that is referred to as the colored complexes, and so it will exhibit a kind of a color, that is the blue color. Okay, so what happens over here? It will show DD transition, hence it is colored in nature. Hence it is colored in nature. Is it clear to you people? Great. Now students, such kind of questions can be asked. You just need to identify whether there is electrons present over there or not, because see what happens if you have configuration from D1 to D9, then yes, there will be DD transition taking place. DD transition will occur over there, will occur in that case, no doubt it will occur. But if I talk about two cases, that means if I am talking about D0 or if I am talking about D10 configuration students, over there at that spot of time there shall be no DD transition. That means it would have no color over there, it would be colorless in nature. So here there is no DD transition. Over here it is no DD transition, and so it is colorless. So these are the questions that they certainly ask you. So you need to write the electronic configuration of the central metal atom, and you need to find out that you need to find the electronic configuration of the central metal atom, and then you need to find out that how many electrons are present over there in the d orbital, okay, in the vacant d orbital that is present outside, or the outermost shell electronic configuration you need to check out, and you need to see that how many electrons are present in d. If there are electrons ranging between d1 to d9 students, then it will show a colored complex. But if it is from d0 and it is d10 configuration, then it will have no color, it will be colorless in nature. Other than this question can also be generally asked, which I have already shown you. Which kind of question? That you need to identify which is a simple salt and which is a complex salt. If it is a complex salt, that means yes, their DD transition will occur. That means electron shall move from lower energy level to the higher energy level, and when the electron will come back from the higher energy level into the lower energy level, it will impart some color because it will emit some kind of energy. Is it clear to you people? Now students, this was all about the colored complexes that you should know over here. Moving on to the next part that we were discussing in the previous lecture was about isomerism. Now if you remember, in the previous lecture we had started what were isomerism, what is isomerism process. So basically iso referred to as same and merism referred to as same molecular formula. Iso basically referred to as same and merism over here refers to as what? Molecular formula. So the one which have same molecular formula is basically referred to as isomerism. Okay, and this process is isomerism, but if we talk about two certain substances over there or two compounds over there and we are going to compare both of them, so they both, if they have the same molecular formula, but yes, there is a difference in their structure, then they are referred to as isomers of each other. Now talking about the very first kind that comes under the category of structural isomerism is about linkage isomerism. See, we had classified isomerisms into two basic categories. If you remember in the previous lecture, I have told you this basic thing that if I divide isomerism, my dear students, into two certain parts, one is going to be the structural isomerism and the another one is going to be the stereoisomerism. And if I talk about the structural isomerism, students, structural isomerism was further divided into four major segments, and if I talk about stereoisomerism, it is further divided into two, that is geometrical and optical. Great, okay. So one of the structural isomerism is linkage isomerism. Now the word itself says linkage. That means we have to see linkage of whom? We have to see the linkage of the ligand towards the central metal atom. That which atom is being linked to the central metal atom. This is the whole case that we need to study over here. Now let us see that what does NCERT says over here. Linkage isomerism arises in the coordination compound containing ambidentate ligand. Now this is really very essential. Ambidentate ligand are the one which have more than one donor site. For example, if I talk about NO2, over here in the case of NO2, we can also take ONO. They are basically ambidentate ligand. How come? If I'm writing NO2 as a ligand, that means nitrogen over here is the donor atom that is donating its electrons and is making a bond with the central metal atom. But if I talk about ONO, that is again NO2, but I have written in a concept where oxygen is now donating its lone pair of electrons to the central metal atom. You have to look over here about the linkage, that which ligand, which atom is linked to the central metal atom. If I talk about NO2, here nitrogen is being linked because nitrogen is donating the electrons. But if I talk about ONO, here oxygen is being linked. Are you getting my point? So basically it arises in which cases? In ambidentate ligand cases. Also you can take example of cyanide and isocyanide, right? If I talk about cyanide and isocyanide again, it is CN and NC. Over here we talk about carbon is being linked, and in isocyanide nitrogen is being linked. Okay, so it is saying that a simple example is provided by the complex containing thiocyanate ligand. Now this is thiocyanate, okay, which may bind through the nitrogen to give. See, now what is happening in this? Basically nitrogen is being bonded to the central metal atom or through sulfur. You can either bond it through sulfur, or you can either bond the ligand to the central metal atom. In this, the ligand here is bonded from the nitrogen atom. That means nitrogen is donating the electrons. Nitrogen is responsible for making a bond with the central metal atom. But over here again the formula is same. It is an ambidentate ligand. So another atom, that is sulfur, that is being bonded over here. See, when I'm talking about this processes, you should know the linkage through which it is linked. Okay, now see, Georgeson discovered such behavior in the complex. Now you have been given one certain example over here which I have already told you, this one. Okay, now let us understand this example. First of all, I shall draw this example over here. You will get my point. See, if I say I have CO, this is central metal atom. Okay, then I have NH3 as my ligand. How many NH3 are attached? Ma'am, 5 NH3 are attached. Then which ligand again? NO2 is the ligand. And then we have an ion, that is Cl2. How many ions? 2. Now how I will represent it, let me show you. What is the coordination number? What will be the coordination number over here? Ma'am, the coordination number shall come out to be 6 because 5 NH3 and 1 NO2. So the coordination number shall come out to be 6. Now let me draw it over here. Okay, I'll draw it over here. See, for example, this is your cobalt. Okay, now see, here I am saying that coordination number is what? Coordination number is, ma'am, 6. So basically an octahedral kind of a geometry will be exhibited, right? And over here now see, 5 NH3 are being linked and 1 is NO2. Now here nitrogen is making a bond. Also there are counter ions such as Cl2 which are present outside. Is it clear to you all? Is it clear to you? This is the initial structure of this one. Now you can also write it in such a way. What will be the isomer of this species? What shall be the isomer of this species? Let us write over here. Just look over here. The isomer of this species shall be CO NH3 5 and then it will be ONO and then it will be Cl2. Are you getting my point? Over here nitrogen is being linked, so we have written NO2, but over here now we have written ONO. That means oxygen is being linked. Is it clear? Okay, now see over here, they have said that it explains such behavior in the complex CONH3,5NO2Cl2, which is obtained as the red form in which the nitrite ligand is bonded through the oxygen. Now in this case you can see oxygen is being bonded, and as the yellow form in which the nitrite ligand is bonded through the nitrogen. Now over here through oxygen and through nitrogen they are being linked and they are forming these two certain kind of isomers over here. Is it clear to you people? So this is all about linkage isomerism. Let us now see the next category. But initially I want you all to write it down so that we can move on to the next part, that is the coordination isomerism. First of all, write it down so that we can start with the next part, that is coordination isomerism. Now see, it is very simple case. First of all, initially let me draw one of the structures and I'll let you know the example. See, if I take an example of Cr NH3 6 and here I have CO CN6. This is your initial first compound. Okay, now what I'm going to do, just observe that what I'm going to do here. Central metal atom chromium is being linked with the NH3 as a ligand with 6 NH3. Here cobalt is being linked with the cyanide, that is the CN. Okay, again if I change their position, now what is happening over here, if this ligand is being replaced by this ligand, so the new compound that will get Cr CN6. Here we shall get CO, NH3 6. So they both will be called as what? Coordinate isomers of each other. They shall be referred to as what, ma'am? They shall be referred to as coordinate isomers of each other. Now let us understand with the definition. See, this type of isomerism arises with the interchange of ligands. Over here we have initially ligand as NH3. Over here we have CN. Now we have interchanged both of the ligands. This ligand is being interchanged by this ligand. Are you getting my point? So which shall you'll get new isomer? This one. Now see. Now they say interchange of ligands between cationic and anionic entities of different metal atoms present in a complex. An example is provided. Now this is the example they have given you, which I have already written over here, in which NH3 ligands are bonded to CO plus 3 and CN negative ligands are bonded to CR plus 3. Its coordination isomer will become this one, where they will interchange their position, which I have already shown you. So this is all about coordination isomerism. Now students, we shall move on to the next part. Kindly write it down. Okay, now we have another example, another type, that is ionization isomerism. What do you refer to as ionization? Ionization referred to as, that means here we shall talk about whom? We shall talk about ions. Now let us understand about which ions. You know that one are the ionizable ions and another one are the non-ionizable ions. So we shall talk about that category. Let us take a certain example, that is if we have CO, NH3, 5, SO4, Br. This is your one of the example. And other than this, now what I'm going to do is, if I'm going to take this bromine ion and I'm going to replace it by the ligand, that is SO4. So I shall get my new isomer, which shall be referred to as ionization isomerism. Are you getting my point? What I am here referring to you people, that students, here we are going to interchange the position of the ion as well as the ligand. So what is happening over here? Ma'am, over here, this Br shall be replaced by SO4. So what shall be the new isomer that we shall obtain from here? We will obtain CO, NH3, 5, Br, SO4. Are you getting my point? Now let us read with the NCERT. This form of isomerism arises when the counter ion. Now what is referred to as counter ion? Counter ion are the non-ion counter ion are the ionizable ones. They are referred to as the ionizable ions, okay? In a complex salt is itself a potential ligand and can displace a ligand, which can then become the counter ion. Are you getting my point? See, if you don't remember, let me give you a certain example. See, if I say over here that we have a over here, and this is central metal atom, this are ligand, this is a number of ligands, and this is the overall charge, and here is one more ion. So this is basically positive, this is basically negative. What were ionizable and non-ionizable ions, if you remember students? M here is your central metal atom. M here is your central metal atom. Okay. L basically is your ligand. L basically is your ligand. N basically is here your number of ligands. N basically is your number of ligands. Okay. Now students, here you have A positive and B negative, which are present outside the coordination sphere. What is coordination sphere over here? Ma'am, coordination sphere over here is the square bracket. This square bracket is basically the coordination sphere. This is basically the coordination sphere. So the ones which are present outside the coordination sphere are referred to as your ionizable ions. That means it will dissociate into its ions. But the ones which are present inside the coordination sphere are the non-ionizable ions. Yes. So here I am talking about which ions? The counter ions or the ionizable ones. That means I shall be talking about which ions? Which are present outside the coordination sphere. So simple. So see what is happening over here. This form of isomerism arises when counter ion in a complex salt is itself a potential ligand. That means it can behave as a ligand. Over here, Br is so much capable that it can itself behave as a potential ligand, and so it can displace this ligand and take its place. And the ligand now will become the counter ion. The SO4 now becomes the counter ion in its isomer form. So these two basically will be referred to as your ionization ionization isomers of each other. Ionization isomers of each other. Kindly write it down, students, so that we can move on to the next part. Now comes the last category, that is referred to as solvent isomerism, or you can also say it as hydrated isomerism or hydration isomerism. Now let us understand over here what does the hydrate isomerism or the hydration isomerism or the solvent isomerism explains us. Let me give you a certain example and I'll let you know first of all. For example, here the central metal atom is Cr and here we have initially water as our ligand. Let us take an example of this. Now over here 6 water molecules are bonded to the central metal atom chromium and we have 3 chlorine as the counter ions which are present outside. That means this Cl that 3 we here have are the ionizable ions. Now if I have to make its hydrate isomer, then how I can make it? What will happen? One water molecule will go outside and one Cl will come inside. So what will happen here? We will get, now see, coordination number should remain same. Here coordination number is how much, ma'am? It is 6. 6 referred to as that, 6 here means that 6 ligands are bonded to the central metal atom. Am I right? So here water, how many H2O? 6. That means 6 are attached to the central metal atom. So if we replace one Cl over here, what shall we get? We'll get H2O 5. One Cl will come inside. So again, now see, 5 H2O and 1 Cl. Coordination number now becomes 6 again. So here, how many will come as counter ions or as ionizable ions? 2 will be chlorine and 1 shall be our water molecule. 2 will be chlorine because 1 chlorine is now behaving as a ligand. Okay, if I have to make one more over here, how it shall look like? It will be Cr. Now there will be 4 water molecules. And if there are 4 water molecules, again we have to maintain its coordination number, that is 6. In order to maintain the coordination number 6, we have already shown 4 water molecules as the ligand that are present over here. How many are left, ma'am? 2 are left. So how many chlorine will come inside? 2 will come inside. Hence, how many will left outside? Initially there were 3. So 1 is left outside. And how many water molecule will come outside? It will be 2. Is it clear to you? Is it clear to you? Now let us read from the NCERT. What does it explains us? This form of isomerism is known as hydrate isomerism. In this case, where water is taken as what? Water is taken as a solvent, is involved as solvent. Hydrate water. It automatically explains that we are talking about water over here. This is similar to the ionization isomer. Almost it is quite simple because here we are taking the counter ion inside and we are replacing it with ligand. So it is quite similar with the ionization isomer, but the difference over here is we shall always be talking about water molecule over here. We shall always be taking ligand as a water molecule. This is the quite basic difference that you can observe in the case of hydrate isomerism. Now see, solvent isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as a free solvent. That means they at least want the water molecule should be there in order to show the hydrate isomerism. Okay, now an example is provided over here. If I talk about this example, which I've already shown you, it is violet in color and its solvent isomerism, the isomer that they have shown, it is grey green in color. This is grey green in color. Is it clear to you? So this ends our structural isomerism topic over here, my dear students. Now we shall proceed to the next isomer, that is the stereoisomer. I want you all to write it down. Now see, stereoisomers have the same chemical formula and chemical bonds, but they have different spatial arrangements. Now if I am talking about which isomerism? Stereoisomers. Stereoisomers or stereoisomerism is the process in which we can say, again, isomer word is there, so that means molecular formula shall remain same. Same molecular formula. This will remain same, no doubt, but there shall be difference in spatial arrangement. That means arrangement in space. Now students, they are further categorized into 2 basic categories. They are further categorized into 2 basic one. One is the geometrical isomerism. One is the geometrical isomerism. Another one is the optical isomerism. Okay, now initially let us start with the geometrical isomerism. Kindly write this first of all, the definition for the stereoisomerism, so that we can start with the geometrical isomerism. If I talk about geometrical isomerism, these are basically seen in heterolytic complexes. And there is a difference in geometry. Here you observe the difference in geometry. Is it clear to you? Is it clear to you, people? Now, if I talk about different complexes, students, if I talk about square planar complex, tetrahedral complex, and if I talk about, the octahedral complex, you may see that geometrical isomer won't exist for the square planar complex. Do that keep in your mind. Is it clear? Is it clear? Okay, students, now we shall take certain cases in which we can tell about geometrical isomers. Let us talk about the coordination number 4th now. If I say coordination number is what? If I say coordination number is 4. Now what shall happen over here? See, I am talking about which geometry? Let us talk about tetrahedral geometry. Or just talk about coordination number 4. If I am talking about a coordination number 4, and if I ask you if the molecular formula is Ma3B, how many structures, how many geometrical isomers you can obtain from this kind of geometry? See how you will make it. You will make it like this. If it is a central metal atom, these are the ligands shall be present over there in such a way that there are 3A and 1B. So will they have any kind of geometrical isomer of this or not? Kindly tell me, will they show any kind of geometrical isomer or not? Just draw one more structure, just replace their positions and do let me know, will there any be geometrical isomer of each other or not? Can you obtain a geometrical isomer of this or not? See, what is geometrical isomer? Again, you have to change the position of the different groups. Okay, if you change the position of this group, let us say this is your central metal atom. Again, ligands are bonded in such a way. Let us take this A over here. Let us take this A. Now, let us write B over here and A over here. Is it same or the different thing? Just tell me this thing. Is it same or the different thing? Ma'am, they are same. They are same. That means there is no geometrical isomer if we have this kind of a molecular formula. If we have this kind of molecular formula, there shall be no geometrical isomer. Here we are talking about coordination number 4. That means we are talking about when there are 4 ligands present over there. Now, if I talk about one more case over here, students, if I say we have Ma2B2, then just draw its structure. This is central metal atom. 4 ligands are attached. Let us take here A, here B, B. Is it clear? This is your first geometry that you can see over here. Okay, can you obtain more structure? Yes, ma'am. Okay, which structure? See, if this is central metal atom, again we have 4 ligands. Now, if I say here we have taken AA. So, let us take this AA over here and this BB over here. So, yes, can you obtain this kind of structure? Yes, ma'am. Are they similar? No, ma'am. Why? Because see over here what is happening. AA lies on the same side and BB are lying on the same side. But over here, A is lying on the diagonal while B is lying on the diagonal. Now, this structure, when 2 same atoms are present on the similar side, it is referred to as your cis structure, and this shall be your trans structure. So, you can obtain geometrical isomer of Ma2B2 structure over here. Yes, very good, very good. Kindly write it down. Kindly draw and write it down. These are the general formulas that I am talking over here. These are the general formula, students, that I am talking. Okay, now if I talk about octahedral complex, that means if I talk about coordination number 6, let us take an example of Ma4B2. Now here, if I refer to as coordination number 6, that means I am talking about how many ligands? 6 ligands over here, 4A and 2B, that means 6. How we shall represent it? We shall say that we have central metal atom over here, and here it shall look like this. 4 will be present in plane and 1 over here, 1 over here. So we can say that if here it is A, and this is BB respectively. Also we can obtain more structures. This is central metal atom like this. So here we can write, if here it is AA, now I am taking 1B over here and 1B over here and is AA. So are they similar? No, ma'am, they are different structures. See, initially what was happening? B was present upside as well as downward. Now here one B is upside and one B is in plane. So these are the, again, different structures over here. So we can say that again they have the geometrical isomers of each other. Is it clear to you, people? Is it clear to you? So over here you can obtain geometrical isomers of each other. Kindly write it down, students. This ends our coordination number 6 over here. This ends our coordination number 6. Okay, one more here of coordination number 6 we can consider. This is MA4B2. No, one more we can consider. Let us talk about MA3B3. If I say MA3B3, AB here are ligands, okay, and M is central metal atom. So if I talk about this is a central metal atom, again we have 6 ligands over here. So here what I will be obtaining, see, if I talk about A is present A, and this is your B, B, B. This is your initial structure. One more that I can obtain over here. This is M, like this. So basically this is A, and this is your B, B, B. See how you can compare, very simple. Just see what is happening over here. They are present in a same phase. See, they are present in a same phase, A, while B, B, B on the one side. Here you can see they are present in plane. Here they are present in a plane, in a plane. Here one is present above the plane and other are in the plane. Here they are present in a plane. Here they are present on the face. So it is referred to as facial, or FAC you can write. Okay, so this is your one kind of isomer that you obtain over here, and the another one is meridional. Okay, facial and meridional. As it is present in face, so it is facial, or FAC we write, and here it is meridional, so we write MER. Is it clear? So these are the two kinds of isomer that you obtain when the coordination number comes out to be what? 6. Again explaining, this is a kind of a 3D structure like this. One atom here, one atom here, one atom here, one atom here, one atom above, one atom below. So this is what happening over here. One atom is above and 2A in the plane itself. Like this, a triangle shall be obtained. So it is a facial because we are talking about a face. But over here it is present in plane. That's why it is meridional. Is it clear? So this was all about the coordination number 6. It is important structure that you can see. Now comes optical isomer. Kindly write it down. Optical isomerism. Mirror images which are not superimposable on each other, they shall exhibit the optical isomerism over here. Now you need to understand what is a superimposable image and what is a non-superimposable image. We need to understand this very basic concept. See, I said that which are not superimposable on each other. That means if I'm talking about this particular hand over here, and if I have this hand over here, if I keep this like this, is it superimposable? You can see that my both of the thumb are not coming on each other. So it is non-superimposable mirror images. Is it clear? We can say not superimposable, or we can also use a word which is non-superimposable. It is one of the same kind. So the mirror images which are non-superimposable, or in other terms I can say which is not superimposable, are referred to as your what? Optical isomerism. Is it clear to you? And they are referred to as enantiomers. They are referred to as enantiomers, and the one which exhibit this basically you can say are the chiral molecules. Now what is a chiral molecule? A chiral molecule or a chiral carbon is referred to as a carbon which contains 4 different groups, is our chiral carbon. Is it clear to you, people? Is it clear to you? This is the optical isomerism concept that you may have done in your chapter haloalkanes and haloarenes in detail. Is it clear? Now students, you have started in that particular segment. We shall move on to our next part. That is going to be the bonding in metal carbonyls. Let us start it. Now you can take the examples of optical isomerism in your NCERT. Examples are certainly given to you. Just you need to understand that here we are talking about non-superimposable mirror images. Now talking about bonding in metal carbonyls, just understand the homoleptic, homo referred to as same. Homoleptic carbonyls, that means compound containing carbonyl ligand, that means CO ligand only. Here we shall be talking all about CO ligand only. Do remember this thing, okay? Are formed by most of the transition metals. Now these carbonyls have simple, well-defined structures, which I will be showing you in the next slide. The metal carbon bond in the metal carbonyl possesses both the kind of character, that is the sigma as well as the pi character. Now understand this thing. The metal carbon, sigma bond is formed by the donation of the electrons, okay, on the carbonyl carbon into the vacant. Now it is donating its lone pair of electrons, but the metal carbon pi bond that is formed, it is formed by donation of a pair of electrons from a filled d orbital of a metal into the vacant anti-bonding pi star. You need to understand how electrons are being donated. In one of the cases, if you observe over here, the donation of lone pair of electrons on the carbonyl compound is done into a vacant d orbital. Now in the another case, if you talk about the pi bond, in this particular, the donation of a pair of electron is done from a filled d orbital into a vacant anti-bonding, pi star orbital. Is it clear? Of the carbon monoxide that we are talking about, okay? The metal to ligand bonding creates a synergic effect basically, which strengthens the bond between the CO and the central metal atom, which you can see from this particular structure over here. Here this is the sigma bond that is being formed, and here this is the pi bond that is being formed. In the case of pi bond, it is moving into the anti-bonding pi star orbital. Is it clear? Now these are the interactions with respect to your carbonyl complex, and this is a kind of a synergic bond. Now students, we shall start our practice sheet questions. So the very first initial question is in front of you. Kindly read the question very carefully and try to solve the questions. So the very first question is, few isomers are given below. Mark the correct statement regarding them. They have provided you with first, second and third respectively. They are the few isomers, and you need to tell which kind of isomerism they exhibit and which kind of isomers are they. So if I talk about the very first case, here we have Cr, H2O, we have 6 ligands over here, and Cl3 as our counter ions. In the second one, we have Cr again as a central metal atom, and again we have H2O, that are the 5 water molecules as the ligand participating over here, and one is the Cl, which is the ligand behaving over here, which was one initially the counter ion, but now it is behaving as what? It has a tendency to act as a ligand, so it is now coming inside and it is replacing one of the water molecules and is becoming a ligand. So the water molecule goes out. Now again one more water molecule will go out and one more Cl will act as a ligand. So this we have just done right down, ma'am. All of these three are basically the hydrate isomers of each other. They are what? They are hydrate isomers of each other, or we can say the process over here is referred to as hydration isomerism or hydrate isomerism or solvate isomerism. Clear? So which of the following options is going to be the correct answer? Let us see. A option is saying first, second and third are hydrate isomers. B is saying first, second and third are coordination isomers. C is saying first, second and third are ionization isomers. And D is saying first and second are stereoisomers of each other. So which of the following will be correct? Option number A will be our correct answer. Great. Clear? Okay. Now comes the next question of your practice sheet. Which of the following pair of isomers is not correctly matched with it type of isomerism? So students, kindly read the question, see the structures and just match them. Which of the following pair is incorrect? So let us see one by one. If I talk about initially the A option over here, they are saying we have Cr as the central metal atom and we have NH3 6 over here as the ligand. So coordination number again is 6. And here we have Cr and we have Cn as 6. Okay, this is the first compound that we have, and the second compound is what is happening. Just see the basic difference in both of these over here. If I look up to the basic difference, initially they are talking about coordination isomerism, okay, and in the second one they are talking about the linkage isomerism. In the third, again they are talking about the coordination, while in the fourth they are talking about ionization isomerism. So you know all the differences. Kindly let me know which of the following is going to be the incorrect answer over here. Kindly do this fast. Kindly do this fast. Let us see what is going to happen. See, in the very first case, coordination isomerism. That means here you have to see the coordination number is 6. Coordination number is 6. Here you can see there is only one ligand that are present, but over here are 4 ammonia and 2 cyanide, 2 ammonia and 4 cyanide. So basically what is happening over here, the number of ligands are being changed. Yes, so they are referred to as coordination isomerism. It is a correct statement. Now let us see the second one. Over here, if you see that CO remains same, NH3 are 5, again 5, Cl2, even the counter ions are same, but here it is written NO2 and here it is written ONO. That means here the ligand which is donating its electrons to the central metal atom, that atom is different. If I talk about NO2, over here in this particular case, nitrogen is donating its lone pair of electron, but if I talk about ONO, over here oxygen is donating its lone pair of electron. That means here the ligand that is being donating its electron is which one? They both are ambidentate ligands. So yes, it is a linkage isomerism because the linkage with the central metal atom is different. Here nitrogen, there oxygen. Great. Now comes the third category. Over here if you see CO, central metal atom, pyridine twice, same. H2O twice, Cl twice. Here H2O is 1 but Cl is 3. Again, when we are talking about water, what is when we take water as our solvent and we talk about the exchange of the counter ions with the water molecule, they are referred to as a solvent isomerism or which one? Sorry, solvent isomerism or which one? Hydrate isomerism. So yes, basically this is wrong because they have written they are coordination isomerism. No, they are basically your hydrate isomerism. So incorrect statement is your option number C. That will be your correct answer. Great. Shall we proceed to the next part? Okay, you can see the option number 4th also. In option number 4th, Cl2 and Br2 are replacing their position. That means the counter ions are being replaced by the ligands and the ligands now shall behave as a counter ion. So yes, they are the ionization isomer because here ionizable ions are being responsible. Let us see the next question that we have with us. Hexaamine nickel twice, hexanitrocobaltate third can be written as. Students, you have 2 minutes. Kindly write its structure. Kindly draw its structure. See, hexaamine. First of all, see, whenever you're doing such kinds of questions and you have been provided with the option, just see the options. Here it is written hexaamine. Hexa referred to as what? 6. Amine, now you know basically amine is what? Your NH3. Hexaamine, that means 6NH3. Let us see 6NH3 in which of the following cases. In all of the following cases, 6NH3. Great. Now, nickel twice. Nickel, that means central metal atom should be nickel and NH3, 6 should be there. This is there, this is there, this is there, this is there. Okay, ma'am. Next. Hexanitrocobaltate. Hexanitro. Hexa again 6. Nitro again what? NO2. Okay. Now 6 NO2 should be there. 6 NO2, 6 NO2, 6 NO2. NO2 6. Great. Cobaltate. Cobaltate, that means cobalt. Here this is wrong. Cobalt is written outside, so this is wrong. Now moving on to the next part. Here they have written the oxidation state of nickel as +2. Here its oxidation state is +2. Over here, if I talk about its oxidation state cobalt, it is +3. It is +3. So the charge on this will come at its base and the charge on this will come at its base. Basically, it have an overall charge of 2 and it have a 3. So 3 charge will come over here and 2 charge will come over here. Hence, option number B is going to be the correct answer. If you feel that, ma'am, we are unable to do so, you can write their names accordingly and you can match with the nomenclature. Great. Now let us see the next question that we have. The next question is, which among the following will be named as dibromido bis ethylene diamine chromium third bromide? Now again, you have to draw the structure. Very simple question. Very simple question. Here they have given you dibromido. That means how many bromine? 2 bromine. See, always remember this thing, students. Always remember this thing, that initially we always write the ligands. That means here bromine is ligand. How many? 2. Here it is 4, so this is wrong. Here it is 2, here it is 2. Here bromine is outside, so this is wrong. Either it can be A or it can be B. Now the next thing is dibromido bis ethylene diamine. What is ethylene diamine? It is written as En. Bis referred to as 2. That means it shall be 2. So En twice. En twice is written over here. Yes. Now again chromium. Okay. And bromide, that means it is iron. So option number A shall be our correct answer. Option number A will be our correct answer. Is it clear? Kindly write this question. Kindly write it down. See, this is the correct identification how you need to find the answers. Shall we move on to the next question of ours? Yes, ma'am. Okay. So the next question is, correct formula of tetraamine chloronitropladinum 4 sulfate can be written as. Tell me fast, what shall happen over here? See, students, here tetraamine again how many? NH3, 4, ma'am. Okay, again then we have chloro-nitroplatinum. Okay, now we have chloro also, that means 1 Cl shall also be there. Let us find out. See, 4NH3, 1 Cl. NH3, 4, there are 2 Cl? No. NH3, 4, 1 Cl. Here, NH3 is 1, so this is also wrong. Either it can be A or it can be your C option. Now, it is chloro, we have done, okay. Nitroplatinum 4 sulfate. Nitroplatinum 4 sulfate. Now see, sulfate, it is present outside, sulfate, it is present outside. It's great. Now we are left with only nitro and with the, the oxidation state as +4. Now you have to tell me which of the following is the correct answer. You have to write in the comment section its answer. Now you have only option number either A or C. It is very simple. So write in the comment section your answer. Is it clear? Shall we move on to the next part? The next part is match the column 1 with the column number 2 and mark the appropriate choice. You need to tell which of the following exhibits which kind of isomerism. Let us see. Let us see. Let us see and find out which of the following can exhibit which kind of isomers. Now see, in this particular case, here, in this particular case, what you can say? Here you can say that, ma'am, this can exhibit coordination isomer. Why? Because we can interchange the ligands position over here. So A option shall match with the third one. A option is matching the third one. Answer is option number C. See, I require I require very initial few seconds in order to solve this question, because there is no need to check all of them. Either if you see one of them, you'll get your correct answer. Now you can even match it out. See, in the next case, here we can say that this Br basically can come inside, and this base, no, not this Br negative will come inside. Here we have NO2. It is acting as an ambidentate ligand, so you can also write ONO over here. That means it is a linkage isomer. So if it is a linkage isomer, it is option number 4th. So B will be referred to as option number 4th. Now if I talk about this C1, basically if I talk over here, it can exhibit which kind of isomer? Here we have En, and we have twice of En, that is ethylene diamine, and it will exhibit optical isomerism. And if I talk about the last one, yes, it will exhibit which one? The geometrical isomerism. Clear? Let us see the next question that we have. Which of the following sets of examples in geometry of the compound is not correct? Now this you have to tell by your own, because we have already done this topic. So this is your question number 2, which shall be referred to as your homework question. Kindly write the homework question, take a screenshot so that we can move on to our next part. Kindly write the question so that we can move on to our next part. Let us see the next question. Mark the correct statements regarding the geometry of the complex ions. Okay. First is, the geometry of the complex ion depends upon the coordination number. Second, if the coordination number is 6, the complex is octahedral. Third, if the coordination number is 4, the geometry of the complex may be tetrahedral or square planar. So you have certain options over here, students. The first option is first, second and third. B option is second and first and second only. C option is first and third, while D option is second and third only. So here, students, I am talking about this particular segment. Understand this very basic thing. The geometry of the complex ion depends upon the coordination number. Yes, it is true statement. It depends upon the coordination number. If the coordination number is 4, the geometry shall be which one? It can be square planar or it can be tetrahedral. If the coordination comes out to be 6, the geometry shall come out to be octahedral. So yes, the geometry is basically dependent upon the coordination number. So that means the first part over here is the correct statement. Now if I talk about the second part over here, if coordination number is 6, the complex is octahedral. Yes, just I right now told you, if the coordination number is 6, the geometry is octahedral. If the coordination number is 4, then the two kinds of geometry can be exhibited over there. One is the square planar, another one is the tetrahedral. So yes, the second statement is also correct. Now if I read the third statement over here, if the coordination number is 4, the geometry of the complex may be tetrahedral or square planar. Again, this is the correct statement. That means first, second and third are the correct answer. That means option number A shall be our correct answer. Is it clear? Great, students. Now moving on to the next question of ours. The complex ion which has no d electrons in the central metal atom is, you have A option as MnO4 minus, B option as CuNH3 6 overall charge plus 3, C is FeCN6 overall charge minus 3, while D is CrH2O6 overall charges plus 3. plus 3. Kindly calculate the oxidation state. First of all, if I talk about Mn, it will be X plus. For oxygen we know it is -2 charge. How many oxygen? 4. And what is the overall charge? -1. So it shall be X minus 8 is equals to -1. X is equals to -1 plus 8. That means X comes out to be plus 7 over here. So the oxidation state over here of Mn comes out to be plus 7. And when you are writing its electronic configuration in plus 7 oxidation state, there is no electrons in the d orbital. Hence there shall be the no dd transition. So option number A shall be our correct answer. If there is no d electrons present over here, so this is our correct answer, because Mn and plus 7 will have no electrons. Great. Let us see the next question that we have. Which of the following shall form an octahedral complex? Which of the following will form an octahedral complex? A option D4 with low spin, B option D8 with high spin, C option D6 with low spin, and D option is none of these. So you need to tell, this is your question number 3 as your homework in the comment section, that which of the following will show octahedral complex. Great. Okay, now let us see the next question of ours. CuSO4.5H2O is blue in color while CuSO4 is colorless due to. Again, A option, pressure of strong field ligand in CuSO4.5H2O. The second reason is absence of water as a ligand, and so the DD transitions are not possible in CuSO4. The C option over here that we have is anhydrous CuSO4 undergoes DD transition due to the crystal field splitting, while the D option over here is color is lost due to the loss of unpaired electrons. So students, just right now I have told you, if I talk about initial, when we were starting the session over here today, I told you this very basic thing, that over here if we have CuSO4 is colorless because they have no DD transition. Why they have no DD transition? Because students, they are basically the simple salt. They are referred to as your simple salts. That's why they won't have any DD transition. Now if I talk about CuSO4.5H2 over here, now basically students, it is not a simple salt, it is a complex salt, or it is a coordination compound. Now if it is a complex salt, it will show DD transition. It will exhibit DD transition. Now if it is exhibiting DD transition over here, that means I can say it has a color. In which kind of a color? Blue color. So what is the responsible phenomena? The ligand water. So which of the following will be correct answer? If you see over here, option number B, that is absence of water as a ligand. Also DD transitions are not possible in CuSO4. Why? Because it is a simple salt, right? So option number B shall be our correct answer. Is it clear to you people? Is it clear to you all? So yes, my dear students, this ends our segment over here also, and this ends our session of coordination compound over here. Now we shall meet in the next lecture with a new chapter of ours, and so I want you all to practice as many as questions as you can. And yes, if you feel any doubt in any of the topic, you can write in the comment section. We shall take the topic in the upcoming sessions of our, and we will be meeting in the next lecture. Okay, so meet you in the next lecture. Till then, keep smiling, keep learning. Thank you so much and have a good day.